Hello! In the last video, we diverted from our previous discussions on projections and engineering drawings to the new topic of mechanisms. We covered the principles of levers, cams, and linkages, and we ended off by discussing the fundamental law of gearing in the context of spur gears. In this video, we will continue on with our discussion of gears, first wrapping up our discussion on gearing train design with spur gears before reviewing other types of gears and their uses. Recall from our last video that the reasons we might want to create a gearing train include to change the speed of rotational motion, to create a mechanical advantage by adjusting torque, and or to change the direction of rotation. We used the fundamental law of gearing to understand how gears accomplish this, and we ended up deriving the formula for the gear ratio between meshing input and output gears. This gear ratio is what we will use in this video to go through various gear set design calculations, as well as the equation relating gear diameter to the number of teeth via the module. Other guidelines that we must keep in mind throughout the design process is that we cannot have fractional teeth on a gear. The module of both the gear and pinion in a gear set must be equal for them to mesh properly. And out of the three main design variables of gear diameter, module, and number of teeth, we can only specify two, and the third is automatically set via the equation D equals M times Z. With all of this in mind, let's try our hand at some gear set design calculations. In this first example, we have the pinion with 13 teeth on the input with an angular velocity of 10 revolutions per second clockwise and an output gear with 70 teeth. We want to know the output gear's angular velocity, which we can calculate using the gear ratio equation I equals omega in over omega out, which is also equal to Z out over Z in. Rearranging for omega out, we end up with omega out equals omega in times Z in over Z out. And if we plug in our given values, we get an output angular velocity of 1.85 RPS, or revolutions per second. Of course, we can't forget to mention the direction. Since this gear is meshed with the input rotating clockwise, the output must be rotating in the opposite direction, counterclockwise, so we will indicate that as well. Our second example is the same setup as the first, but now we know the desired output torque of 2 Newton meters, and we want to determine the required input torque for this gear set. As before, we will use our gear ratio equation, specifically I equals tau out over tau in, which is also equal to Z out over Z in, and we will rearrange for the input torque tau in. This gives us tau in equals tau out times Z in over Z out. And if we plug in our givens to solve, we end up with 0.37 Newton meters as our input torque. If we flip this problem around and start with the required input and output torques of 0.18 Newton meters and 1 Newton meters respectively, we can calculate our gear ratio as I equals tau out over tau in, which is 1 over 0.18 equal to 5.55. If we want to determine how many teeth we need on each gear in this case, we know that we want the ratio of the number of teeth to be exactly equal to the torque ratio, but with the requirement that both gears must have a whole number of teeth. We can use our calculators to rewrite the ratio 1 over 0.18 as a ratio of two whole numbers, as 50 over 9, and that could be one possible solution for the number of teeth on each gear. Now, having only 9 teeth on the input gear might be too low, so we might try another tooth ratio instead, like 61 over 11, which yields a gear ratio of 5.545 instead. In some cases, we might not be able to get our gear ratio spot on when considering other constraints like the number of teeth, at which point we have to use our engineering judgment. Finally, let's calculate the center distance of the original 13 to 70 tooth gear set that we considered if we set the module equal to 2 millimeters. Recall that the center distance is the sum of gear and pinion radii, A equals R1 plus R2, and the radii can be computed from the number of teeth and module according to the formula D equals mz. Specifically, the radii are half the diameter, so R equals m times z over 2. This means that A is equal to m times z1 over 2 plus m times z2 over 2, and if we plug in all of our values, we get a center distance of 83 millimeters. In all of these examples, we have considered a single gear set with 2 gears. However, many gear train mechanisms are made of many more gears. One option is to have multiple gears meshed in series, as seen in the top diagram. In this alignment, the intermediate gears called idlers do not have any impact on the overall gear ratio between the input and output gear. They only serve to change the direction and transfer the motion across a greater distance. Our second option is to mount multiple gears axially on a common shaft, as shown in the bottom diagram here, and this is called compound gear design. Such an arrangement allows for larger speed and torque manipulation in a gear train. Let's investigate these two arrangements in the context of design calculations to solidify our understanding. First, we'll look at 3 gears meshed in series with diameters of 10, 20, and 5 millimeters. We are told that the first gear rotates at 1 RPM clockwise, and we want to figure out the output gear's angular velocity, omega 3. We know that the overall gear ratio of a gear train is equal to the input velocity over the output velocity, and we can calculate this overall gear ratio of the train by multiplying the ratio of meshing diameter pairs. I equals d2 over d1 times d3 over d2, which is the same as d3 over d1. In this case, it gives us an overall gear ratio of 0.5. Since our gear ratio I is equal to omega in over omega out, or omega 1 over omega 3 in this case, rearranging and solving for omega 3 gives 2 RPM. Finally, we need to specify the direction. Since all of these gears are meshing, if the first gear rotates clockwise, then the second gear must rotate counterclockwise, and the third must rotate clockwise again, so we will specify that as well. Now let's consider an alternative compound gear train arrangement where gears 1 and 2 are meshed with diameters of 10 and 20 millimeters respectively, and then gears 2 and 3 are axially connected, and gears 3 and 4 are meshed with diameters of 5 and 20 millimeters respectively. If the input gear 1 rotates at 1 RPM clockwise and we want to calculate the resulting output gear 4 angular velocity, we can do so through calculation of the overall gear ratio again, which is equal to the ratio of the input velocity over the output velocity. In the compound gear train case, we again calculate the overall gear train ratio by multiplying the ratio of meshing diameter pairs, which in this case is I equals d2 over d1 times d4 over d3. Note that d2 and d3 are not meshing, so we don't have a ratio for that pair. This gives us a gear ratio of 8, and since our gear ratio is equal to our input speed over our output speed, rearranging for our output speed of omega 4 gives 0.125 RPM. Again, we can't stop there, we still have to indicate the direction of rotation. So if the first gear rotates clockwise, then the second and third gears must rotate counterclockwise, since gear 2 is meshed with gear 1, and 2 and 3 are axially connected, and this means that gear 4 rotates clockwise. So we will indicate that along with our speed. As mentioned before, the compound gear arrangement allows for larger speed and torque manipulation in a gear train, and it is often required when we have constraints on allowable gear size. For instance, consider the example where we want to transform an input speed of 120 RPM to an output speed of 30 RPM under the constraint that all gear diameters must be between 10 and 30 millimeters. We won't consider direction here, just the speed. This gives us a gear ratio of 120 over 30, which is equal to 4. We could try to design a simple gear set with this gear ratio, meaning the ratio of our 2 gear diameters would be equal to 4. But say if we choose our input gear diameter to be 10 millimeters, according to the minimum gear diameter constraint, then the output gear diameter would have to be 40 millimeters, which violates our maximum allowable gear size. Adding intermediate gears in series won't help us here. What we need to do instead is design a compound gear train. One possible solution would be to design 2 gear sets, with the second and third gears connected axially as in the previous example. If we do so, we could have each gear set have a gear ratio of 2 to give our overall gear ratio of 4. This way we could make all of our gears 10 and 20 millimeters, which stays inside the gear size constraints. In this week's lab lesson, we'll go through additional gear train design examples for even more practice, but for now, let's shift our focus to other gear types. Remember that spur gears are just one category of gears at our disposal. To select an appropriate gear type for an application, we should consider key aspects of the problem at hand, including the desired gear ratio, space constraints, and the orientation of the input and output shafts. Each gear type has its own advantages and disadvantages, So we'll take a brief look at each to see what sorts of applications they are suited for. To start, Spur Gears are advantageous in that they are low cost because they are easy to design and manufacture. They are also highly efficient, and they are well suited to low-speed applications where the input and output shafts are parallel. Some disadvantages of Spur Gears is that they aren't suited for any other orientation of input and output shafts, they have limited operating speeds, and the gear ratio is directly related to gear size. So if we want to achieve a large gear ratio, we'd either have to use a very large gear meshed with a very small pinion, or we'd have to use many reasonably sized gear sets in a compound configuration. When it comes to dealing with non-parallel drive axes, alternative gear types better suited to such applications include helical and bevel gears. Both of these types of gears follow the same gear ratio principles as spur gears and have the same kinetic behavior, but helical gears can mesh at any angle, and the conical shape of bevel gears means that they mesh with their shafts perpendicular. Also, the inclined teeth of helical gears offers more gradual tooth engagement for smoother operation, which makes them useful for higher speed applications like in automotive transmission systems. With both helical and bevel gears, their key difference from spur gears is that they have higher axial loading on shafts, but this is really outside of the scope of this course. Another gear type that has perpendicular input and output drive axes is the worm and worm gear. You can think of the worm as a gear in the form of a screw, and it always drives the worm gear. The greatest feature of the worm and worm gear design is that it is capable of very high speed reductions going from the worm's input axis to the worm gear's output axis. In this arrangement, the worm or screw thread meshes with the worm gear's teeth. A worm gear can have one or more threads, but we'll consider a worm with a single thread only. If we recall the gear ratio calculation for meshing spur gears, the gear ratio is equivalent to the ratio of number of teeth on the output and input gears. Since the thread of the worm meshes with the worm gear, and we are considering worms with only a single thread, this is like having a gear with a single tooth. This is how worm and worm gears can achieve such large speed reductions. It should be noted, though, that pitch diameter of the worm is not a function of the number of threads, or teeth. So with worm and worm gears, we can only relate the gear ratio to the angular velocity ratio and to the ratio of gear teeth to worm threads. We cannot relate it to diameters. Let's look at an example to appreciate how large of speed reductions are achievable with this gear type. Say we have a single thread worm spinning at 1000 RPM, meshed with a 50-tooth worm gear. To calculate the worm gear angular velocity, we can use our worm gear ratio equation and rearrange for omega g, which is the angular velocity of the worm gear. If we do so, we will find that the output speed is 20 RPM. That's a speed reduction ratio of 50, which is pretty large for a compact two-gear design. And this illustrates how the compact design makes worm drives ideal for applications where we want a substantial speed decrease. If we had tried to achieve this ratio with spur gears instead, we could pair an input pinion with an output gear 50 times the pinion's diameter, which would be a terrible design. Or we could try out a compound gear train design, for example, a 6-gear train composed of 3 gear sets with individual gear ratios of 5, 5, and 2. This might be better than our first option, but it is still a lot more cumbersome than the simple worm and worm gear design. The last gear type we'll consider in this video is the rack and pinion, which converts rotational motion of the pinion into linear motion of the rack. In this case, there is no gear ratio since the rack doesn't rotate, but we can calculate the linear output speed of the rack by equating it to the tangential linear speed of the pinion. For example, if we had a pinion spinning at 3 revolutions per second, or RPS, and we wanted a rack velocity of 100 millimeters per second, we could determine the required pinion size according to the equation V-rack is equal to V-pinion, or 2 pi times omega r for the pinion, where 2 pi is a unit conversion factor to go from revolutions per second to radians per second. Rearranging, we get that the radius of the pinion is equal to the linear velocity of the rack divided by 2 pi times the angular velocity of the pinion. Plugging in our givens and solving, we can find that the required pinion radius is about 5.3 millimeters. So we've covered quite a bit in this video, from spur gear design calculations to discussion of other gear types, including helical and bevel gears, worm and worm gears, and rack and pinion mechanisms. More design examples will be provided in this week's lab lesson, which will give you all the tools needed for your individual design project. Now that we've talked about mechanisms such as gear trains, where multiple parts are assembled together to accomplish some objective, we can transition into our next topic of assemblies.